Hello, hi guys, myself Mubarak. So in this lecture we are going to discuss about the Birch reduction. So before starting about the first Birch reduction, the first thing to note is that when lithium or sodium dissolves in ammonia, they give an intense blue color solution. So you can see here, so this is the solution of the lithium in liquid ammonia. So you can see very intense blue color solution. The reason for the very intense blue color solution is the solvated electrons. Electrons got solvated here. So I will explain what is meant by the solvated electron by the chemical reaction. I'll start with the lithium. Suppose if you are having the lithium, so when a lithium metal dissolves in water, the lithium atom will get ionized to form the lithium ion and it will liberate one electron. So this electron will get trapped in the cavities of the number of ammonia molecules. You can see here. So this is the cavities which is presenting between the ammonia molecules. This is the solid structure of the ammonia. Okay, so in these cavities or the right shape and right gap, so where electron will get trapped, so in the cavities of the ammonia. So because of this free electrons which is trapped between the cavities of the ammonia molecule, so this solution will get an intense blue color solution, and we can consider this solution as a paramagnetic solution. So readily, whenever you're dissolving the lithium in liquid ammonia, so it forms an intense blue color solution. It is a very fast reaction. So with time, the blue color fades as electron reduces the ammonia to the NH2 minus. Slowly the blue color will fade. And why? Because the ammonia will get reduced to NH2 minus and it liberates the H2 gas. So after some times the solution will become the colorless. Now in the Birch reduction, we'll use the blue solution with the solvated electron as a reducing agent. The reduction of ammonia to the NH2 minus and H2 is quite slow, and a better electron acceptor will get reduced in the preference. So before ammonia was getting reduced to the NH2 minus, if we are adding any substrate so which can accept the solvated electron, so this liquid ammonia will reduce that substrate. For example, if we take the benzene, in case of the benzene, so benzene easily accepts this electron. So this electron will enter into the lowest unoccupied molecular orbital of the benzene. So coming to the Birch reduction, a Birch reduction is an organic reaction that is used to convert an arenes into cyclohexadienes. So you can see an arene here. So what is meant by arenes? And all the aromatic compounds, we can call it as an arenes. So arenes will get converted into the cyclohexadienes. So in this example, we have converted the benzene to the cyclohexadiene. In the second example, we have converted the naphthalene to its corresponding cyclohexadienes. The reaction is named after the Austrian chemist called Arthur Birch. So this is an organic reaction of an aromatic ring in liquid ammonia with the sodium or lithium or potassium and an alcohol such as an ethanol or tertiary butanol. This reaction is different from the catalytic hydrogenation, in which the aromatic ring reduces the cyclohexane. So if you want to do the reduction with the hydrogen in presence of the nickel, so there is the complete reduction. So here the benzene will get completely reduced to the cyclohexane. But in case of benzene reacting with the sodium in presence of liquid ammonia and you are using any solvent like any ethyl alcohol or isopropyl alcohol, so it is a partial reduction. It's not the complete reduction, it's a partial reduction. So coming to the mechanism of the reaction, the first step is the solvated electron enters into the lowest unoccupied molecular orbital of the benzene to form the radical anion. So you can see, so once lithium was dissolved in the liquid ammonia, it forms the Li ion as well as a solvated electron. Now you can see the pi bond will polarize to any one side. Because of the polarization, you can see one carbon you got the negative charge here, the same time you will get the positive charge on this carbon. Now here you will get the negative charge and positive charge here. So this electron will given to this carbon and it will convert into the radical anion like this. So between this positive and negative charge you will get the double bond. This is a newly formed double bond. So you got one radical anion. So this reaction mechanism will proceed to the radical anion as an intermediate. This was proved by ESR spectroscopy, that is electron spin resonance spectroscopy. The radical anion is very basic and it picks up the proton from the ethanol from the reaction mixture. So you can see along with the ammonia we are also using the ethanol. So this ethanol will get ionized to form the sodium ethoxide as well as the H+. So now this radical ion will pick the proton from the ethanol, and so lithium comes along with the sodium ethoxide in the form of the lithium ethoxide. Now the molecule is no longer an anionic, but you can see that still you are having the free radical here. So this free radical picks an electron from the lithium which pair up with the radical to give the another anion. So you can see here, so this free radical have picked an electron from the another sodium atom and you got one anion here, so which is quenched again by the proton to form proton source like the ethanol. So now after anion is formed, this anion will accept the another proton from the ethanol and you will get one neutral molecule. We will call it as cyclohexadiene. Clear? So you can see the two new hydrogens we have added. These two new hydrogens we have added. These two new hydrogens was came from the ethanol. So how many molecules of ethanol we have used in this? So two molecules. So two molecules of ethyl alcohol was consumed here. And how many atoms of sodium was consumed? So two atoms of sodium was consumed. So what is the byproduct here? So you will get the sodium ethoxide as the byproduct. So we have added the total 2 electrons here, so to convert a benzene into cyclohexadiene. So coming to the regioselectivity, if you are having the substituent, so an electron withdrawing substituent leads a product where it bonds to the saturated carbon atom. Suppose if you are having the electron withdrawing group, so what is meant by an electron withdrawing group? So either you call the -M group or you call it as the -I group. A lot of examples are there. COOH is a -I group and NO2 is -I group. Okay, aldehyde is the -I group. So all the electron withdrawing group. So if it is participating in the Birch reduction, suppose I'm taking the reagent here, so sodium in liquid ammonia, so along with this I have took the solvent like ethyl alcohol. So here the substituent will be bounded to the carbon, so which is an sp3 hybridized, that is a saturated. So you can see here, so you will get this type of product, sp3 hybridized carbon. Suppose if you are having the electron releasing groups, so groups like the +M or +I group, for example like OCH3, so methoxide, or like the methyl, or like the aniline. So all this, the substituent will be attached to the saturated carbon atom, that is sp2 carbon atom. So if you are having the electron withdrawing group, so you will get the cyclohexadiene, this type of structure, and if you are having the electron releasing groups, you will get the cyclohexadiene, so in this type of structure. For example, you can see some reactions here. So benzoic acid, when it participating in Birch condensation Birch reaction, so what will be the product? So COOH is -M group. So product you can write here, since -M groups around the carbon which is attached to the -M group, it will be the sp3 carbon atom. So product is this. So you will get this. Suppose in case of the anisole, so here you can see the OCH3, so which is the +M groups, an electron releasing group. That substituent will be attached to the carbon, so which is sp2 hybridized or which is an unsaturated. So you will get the product like this. For example, in case of the nitrobenzene, so nitrobenzene, whenever it participates in the Birch reduction, so nitrobenzene is an electron withdrawing group. So in the case of electron withdrawing group, that electron withdrawing group will be bonded to the saturated carbon atom, and product is this. Suppose if you're having this molecule, so where you're having the two types of substituents on the benzene ring, so here you can see OCH3, so which is OCH3, which is a plus M group, electron releasing group, and COOH, which is an electron releasing group, that is a minus M group. And so product will be like this. That means electron releasing group should have the bond, unsaturated double bond on it, and electron withdrawing group will have the saturated bond like this. Suppose if you are having the molecule, like if you are having the electron releasing group and electron withdrawing group ortho to each other, so product is this. So electron releasing group will have okay, so now electron releasing group will be attached to the double bond, and electron withdrawing group is attached to the sp3 carbon atom. So now in this example also you are having the electron releasing group, there is a plus M group, and electron withdrawing group minus M group para to each other. So product is this. So when you are having the electron releasing group and electron withdrawing group para to each other, so you have to write the product according to the electron withdrawing group. So product should be written according to the electron withdrawing group. For example, here you can see, so this molecule, so when it participated in the Birch reduction, so first you will get this, already I have written, the product is this. Electron releasing group will get an unsaturated double bond, and electron withdrawing group will be attached to the saturated carbon atom. So to this if I add the proton, so this is the 1,4 unsaturated system, so it will convert into the conjugated system like this. In presence of acid medium, they will get isomerizes to give a conjugated system. Suppose in case of the aniline, that isomerization can't be stopped. Why? Because the high activity of the aniline. So direct the product first of all, you will get the 1,4 diene. This 1,4 diene will automatically get isomerized to form the 1,3 diene. Okay guys, this is about the Birch reduction. Still, the sodium in liquid ammonia or lithium in liquid ammonia has a lot of applications. It even can reduce the triple bonds. It even can reduce the alpha beta and saturated carbonyl compounds. That we'll discuss in the next lecture.